SpaceX SuperDraco. SuperDraco is a hypergolic propellant rocket engine designed and built by SpaceX. It is part of the SpaceX Draco family of rocket engines. A redundant array of 8 SuperDraco engines provides fault-tolerant propulsion for use as a launch escape system, LES, or launch abort system, LAS, for the SpaceX Dragon 2, a passenger-carrying space capsule. SuperDraco rocket engines utilize a storable, non-cryogenic, hypergolic propellant which allows the engines to be fired many months after fueling and launch. They combine the functions of both a reaction control system, RCS, and a main propulsive engine. Hypergolic fuels do not require an external source of ignition, providing increased reliability for the spacecraft. The engines are used on crew transport flights to low Earth orbit, LEO, and were also projected to be used for entry, descent and landing control of the now-cancelled SpaceX Red Dragon to Mars. SuperDracos are used on the SpaceX Dragon 2 crew-transporting space capsule and were used on the Dragon 2 Dragonfly, Dragon C201, a prototype low-altitude reusable rocket that was used for flight testing various aspects of the propulsive landing technology. While the engine is capable of 73,000 newtons, 16,400 pounds force of thrust, during use for Dragonfly testing, the engines were throttled to 68,170 newtons, 15,325 pounds force, to maintain vehicle stability. SpaceX originally intended to use the SuperDraco engines to land Crew Dragon on land. Parachutes and an ocean splashdown were envisioned for use only in the case of an aborted launch. Precision water landing under parachutes was proposed to the National Aeronautics and Space Administration, NASA, as the baseline return and recovery approach for the first few flights of Crew Dragon. The plan to use propulsive landing was later cancelled, leaving ocean splashdown under parachutes as the only option. In 2024, the use of the SuperDraco thrusters for propulsive landing was enabled again, but only as a backup for parachute emergencies. History. On February 1, 2012, SpaceX announced that it had completed the development of a new, more powerful version of a storable propellant rocket engine, this one called SuperDraco. This high-thrust hypergolic engine, about 200 times more powerful than the SpaceX Draco RCS thruster hypergolic engine, offers deep throttling ability, and just like the Draco thruster, was designed to provide multiple restart capability and use the same shared hypergolic propellants as Draco. Its primary purpose was to be for SpaceX's launch abort system on the Dragon spacecraft. According to a NASA press release, the engine has a transient from ignition to full thrust of 100 milliseconds. During launch abort, 8 SuperDracos were expected to fire for 5 seconds at full thrust. The development of the engine was partially funded by NASA's Commercial Crew Development Phase 2, CCDEV-2, program. Name: Draco comes from the Greek drakon for dragon. Draco, constellation, is a constellation, the Dragon, in the polar region of the northern hemisphere near Cepheus and Ursa Major. Design. SpaceX SuperDraco engines use a storable propellant mixture of monomethyl hydrazine, MMH, CH6N2, fuel and dinitrogen tetroxide, N2O4, commonly referred to as nitrogen tetroxide, NTO, oxidizer. They are capable of being restarted many times, and have the capability to deeply reduce their thrust, providing precise control during propulsive landing of the Dragon capsule. SpaceX SuperDraco is the third most powerful engine developed by SpaceX. It is approximately 200 times as powerful as the SpaceX Draco thruster engine. By comparison, it is more than twice as powerful as the SpaceX Kestrel engine that was used in SpaceX's Falcon 1 two-stage small-lift launch vehicle second stage, about 1 to 9 the thrust of a Merlin 1D engine, and expected to be 1 to 26th as powerful as the SpaceX Raptor engine. In addition to the use of the SuperDraco thrusters for powered landings on Earth, NASA's Ames Research Center, ARC, also known as NASA Ames, was studying the feasibility of a Dragon-derived Mars lander, SpaceX Red Dragon, for scientific investigation until 2017. Preliminary analysis in 2011 indicated that the final deceleration would be within the retropropulsion SuperDraco thruster capabilities. SpaceX SuperDraco is designed to be highly throttleable, from 100 to 20% of full thrust. This would have been used for precision controllable propulsive landings of the SpaceX Dragon version 2 spacecraft. Engine testing. The SuperDraco engine development program had an extensive test program that spanned several years. As of December 2012, the SuperDraco ground test engines had been fired a total of 58 times for a total firing time duration of 117 seconds, and SpaceX expressed hope that the test results would exceed the original requirements for the engine. A second version of the engine was developed in 2013, this one manufactured with 3D printing, also called additive manufacturing, rather than the traditional casting technique. By July 2014, the 3D printed engine combustion chamber had been fired over 80 times, for a total duration of more than 300 seconds, and it likewise completed a full qualification test. The SpaceX SuperDraco completed qualification testing in May 2014, including testing across a variety of conditions including multiple starts, extended firing durations and extreme off-nominal propellant flow and temperatures. By January 2015, SpaceX demonstrated the SuperDraco engine pod with full functionality at McGregor, Texas. 4 of these engine pods, each containing 2 SuperDraco engines, will be used in the SpaceX Dragon 2 crewed spacecraft. In April 2015, SpaceX and NASA set a timeframe to test a Dragon 2's SuperDraco engines with a pad abort test, PAT. The test eventually occurred on May 6, 2015, from a test stand at Cape Canaveral Air Force Station, CAFS, Space Launch Complex 40, SLC-40, sometimes referred to as Slick 40, and was successful. On April 20, 2019, the SpaceX Crew Dragon capsule used on the Demonstration Motor 1, DM-1, was destroyed during a test of the SuperDraco engines at Landing Zone 1, LZ-1. Manufacturing. On September 5, 2013, Elon Reeve Musk tweeted an image of a regeneratively cooled SpaceX SuperDraco rocket chamber emerging from an EOS 3D metal printer, and indicated that it was composed of the NKNL superalloy. This was later shown to be the production technique for the flight-level engines. It was announced in May 2014 that the flight-qualified version of the SuperDraco engine is the first fully 3D printed rocket engine. In particular, the engine combustion chamber is printed of NKNL, an alloy of nickel, chromium, and iron, using a process of direct metal laser sintering or selective laser sintering, SLS, and operates at a chamber pressure 6,900 kilopascals, 1,000 pounds per square inch, at a very high temperature. The engines are contained in a printed protective nacelle to prevent fault propagation in the event of an engine failure. The ability to 3D print the complex parts was key to achieving the low-mass objective of the engine. According to Elon Musk, it's a very complex engine, and it was very difficult to form all the cooling channels, the injector head, and the throttling mechanism. Being able to print very high-strength advanced alloys was crucial to being able to create the SpaceX SuperDraco engine as it is. The 3D printing process for the SuperDraco engine dramatically reduces lead time compared to the traditional cast parts, and has superior strength, ductility, and fracture resistance, with a lower variability in materials properties. According to Elon Musk, cost reduction through 3D printing is also significant, in particular because SpaceX can print an hourglass chamber where the entire wall consists of internal cooling channels, which would be impossible without additive manufacturing.